welcome back. This is going to be the final lecture of this course by Professor Müller. Bernhard, please take it away.
Yes, thank you. Okay, can you see my screen?
Yes.
I'll go to full screen now. All right. Okay, so last part of the journey, at least as far as the core collapse supernovae are concerned. So what's on the program for today? We're going to pick off where we left off last time. So we discussed last time the nucleosynthesis in massive stars during the hydrostatic burning stages. We're going to see what that does, what follows during the explosion, and afterwards we'll dig a bit into the topic of supernova observations, just taking as much time as we can afford. We're very limited in that, of course, but I hope you still get something out of it. And yes, let's see what's in there. You've had a very, very dense week, and I must congratulate you on your perseverance in this chase through a number of different topics in core collapse supernova theory, and of course the other lectures at the same time and the tutorials. So yeah, congratulations if you can stick through this course and ingest all of that, or just some part of it actually. All right, so let's see what happens after the collapse with the nucleosynthesis. So we're left with what the various core and shell burning stages have produced. We've discussed that last time. And now a few things are going to happen with this material during the explosion. Yeah. On the one hand, so we're going to modify the material that we've synthesized so far for different reasons. So on the one hand, material that makes it very close to the neutron star, that actually drops into this gain region and is then re-ejected, will be completely reprocessed by neutrino heating. It will be broken up into neutrons and protons initially, and then the neutron and proton ratio will be reset by the neutrino heating, and the entropy will be reset by the neutrino heating. And when it's ejected, what comes out in this innermost region depends primarily on the exposure to neutrinos there. Now, material further out will not be affected by the neutrinos much, might be affected by to a small degree. We'll see that under item number 3, but it will still be run over by the shock. And if the post-shock temperatures are high enough to trigger another nuclear burning stage, then we get what is known as explosive burning, and we reprocess the material simply in these shells affected by that, according to the maximum temperature that we reach, and according to the expansion history thereafter. And finally, the neutrinos that come out through these outer shells, that pass these outer shells, they will not do much there in terms of affecting the thermodynamics and the dynamics of this material, but there is, for some nuclei, the chance that some of the higher energy neutrinos in the tail of the distribution of what was emitted in the core will do some reactions on these nuclei. These might be absorption reactions, or they might be spallation reactions. So, for example, you can make some rare isotopes like beryllium-10 there by spallation of carbon-12 if you hit that with a neutrino of sufficiently high energy. Yeah. So what's going to be of interest to us, at least in terms of a more detailed discussion, are those two components here, the explosive burning and the neutrino processed material. You'll only see the results of these other neutrino processes further out in the envelope at the end when we assemble all the yields together. And let's discuss explosive burning first, because in a sense, that's the simplest thing. You don't really need to know about the exact neutrino emission. You just need to know about the energetics of the explosion. Yeah. So what is explosive burning determined by? Well, of course, it's determined by what you have as fuel. Yeah. That determines the threshold temperature for any further reactions that might take place. So in order to further reprocess oxygen, for example, you'll need higher post-shock temperatures than to reprocess carbon. Then the next important parameter is the peak temperature behind the shock, right after the material is shocked. So you can do a very crude approximation of that by equating the explosion energy with the thermal energy of the material inside the shock at a given time when the shock has just reached that particular radius. And you can get a rough estimate of the post-shock temperatures there in terms of the explosion energy and the radius of the shock. Yeah. Now, what's matters also is not only the post-shock temperature, it's also the density, the post-shock density, and through the density, the entropy. That's closely related to each other, because the post-shock entropy will, for example, dictate in nuclear statistical equilibrium how many alpha particles you get compared to heavy nuclei and so on, and that's going to shift some of your nucleosynthesis yields. To good order, the entropy, as we know, is determined by the ratio T cubed over rho, and the post-shock density, luckily, is always closely related to the pre-shock density. There's a relatively fixed compression ratio, which varies slightly depending on the exact equation of state regime that you're in behind the supernova shock, and depending on how much energy you liberate by explosive burning. But the post-shock to pre-shock density ratio tends to be of the order of a few always. Yeah. No matter how strong the shock really is, that's a beautiful, beautiful result from hydrodynamics, the hydrodynamics of shocks. The compression ratio never goes to infinity for adiabatic shocks. Then another parameter that matters crucially is how fast the material expands and cools after it has been shocked. So intuitively, that makes sense, because if the material only stays hot enough for nuclear reactions for a short time, then you expect that less reprocessing can be done, of course. Yeah. This is conveniently parameterized by the expansion timescale, so an e-folding timescale for density or temperature. And for explosive nucleosynthesis, the expansion timescale will tend to be of order of the nuclear burning timescale typically. And then what you tend to get afterwards, because the material behind the shock very soon starts to expand homologously with a Hubble expansion law, velocity proportional to radius, you tend to get basically a power law decline of temperature and density. So these are the raw parameters that will determine our nucleosynthesis. Now let's look at the consequences from a more phenomenological point of view. So basically, you're going to do, depending on the threshold temperature, very similar nucleosynthesis as in the hydrostatic burning phases. The only difference is that the threshold temperatures for explosive burning tend to be higher. That's simply because the timescales for burning in explosive burning are much shorter compared to hydrostatic burning. Yeah. And that's why you need somewhat higher threshold temperatures to ignite a certain burning stage. Yeah. The situation can become, however, a little more complex for silicon burning when you compare that to the hydrostatic burning stages, because, well, the thing here is that for complete silicon burning into NSE, what will also matter is that you're now burning with a different neutron excess than during hydrostatic silicon burning. Yeah, we'll see what the effect of that is. So that's basically what will dictate that we make most of the iron group material in a core collapse supernova initially as nickel 56 and not as iron 56. All right. Yeah. So what will happen is that the carbon, neon, oxygen burning are basically these burnings started by two particle reactions, carbon 12 and carbon 12, oxygen 16 or oxygen 16 in their side chains, and neon is dissociation. And the silicon burning has this quasi-equilibrium nature that we already discussed yesterday. Yeah. And at the highest temperatures, the silicon burning, of course, leads to nuclear statistical equilibrium. Now let's review this concept of nuclear statistical equilibrium or quasi-equilibrium a bit more. This is both, yeah, there's a typo in here. This is both relevant really for the 1A supernovae, the thermonuclear ones, and the core collapses. The nuclear statistical equilibrium, as you know, is dictated by the Saha equation. Should briefly comment on a question in the chat. There's some background noise here on my side. I apologize for that. Someone on this floor is making some repairs outside, so I hope my voice is still clear enough for you to understand. If I need to repeat something, please let me know. Yeah, this is unfortunate when you're doing these things from home. Yeah. All right. So what dictates NSE abundance? Yeah. So the NSE abundance, or also the quasi-equilibrium abundance, when the alpha particles are not in complete equilibrium, is dictated by a Saha equation. Let's maybe move on directly to this slide here. So in nuclear statistical equilibrium, complete nuclear statistical equilibrium, we have a Saha equation that relates the number densities of neutrons and protons to the number density of any heavy nucleus. Yeah, and what comes into play there is the Boltzmann factor exponential of the mass excess, a difference in binding energy over kT. Yeah, and this theta factor here, which contains the thermal wavelength of the particles. Yeah, and I think there's a typo in here. This should be taken to the power of n. Yeah, and yeah, that's what decides about the equilibrium abundances in nuclear statistical equilibrium. This happens under the constraints that the neutron to proton ratio tends to be fixed, relatively fixed, because that only changes by weak interactions on much longer time scales. Yeah, so this will be determined by the neutron excess. You typically have a neutron excess. You sometimes can have a proton excess in the neutrino-driven ejecta. We'll get into that later. We can't solve this equation here easily analytically, but I can basically point you to the overall behavior that this that the nuclear statistical equilibrium will exhibit. So basically what will happen, and it's probably useful if I make a sketch here. So as long as the entropy, switch background. So as long as the as long as the entropy of the material is low, you will tend to select on the nuclear chart, you will tend to select a nucleus with high binding energy. Yeah. And on the other hand, this nucleus with high binding energy, if I draw a sketch of the nuclear chart, yeah. So on the other hand, you'll have for a given neutron excess, you're basically fixing here the ratio of protons to neutrons equals constant here. Yeah, and you'll not select the nucleus with the absolutely highest binding energy at low entropies with the highest Boltzmann factor, but you're going to select primarily a nucleus that has the highest binding energy on a line Z over N corresponding to your proton to neutron ratio. Yeah, and if you do that either in a core collapse supernova with the material, let's say, outside the initial iron silicon core, or also in a thermonuclear supernova, your initial YE is probably going to be close to 0.5. And under these conditions, you actually choose a nucleus you have to choose a nucleus which is actually not stable, yeah, but still has sort of maximizes the binding energy for these conditions of YE 0.5, and that's nickel 56. Yeah, so this explains this rough phenomenology of NSE at low entropy, explains why you make mostly by nuclear burning in complete silicon burning, why you make nickel 56 primarily. Yeah, and not any stable ion group element right away. All right. Now, if you have, and we'll actually come to this, if you have NSE or complete silicon burning into NSE at different neutron excess, and that would happen, for example, if you do incomplete silicon burning in your silicon shell around the iron core and not of the material further out. So if you don't burn oxygen into NSE, but the silicon inside closer inside your core, which tends to have a slightly a higher neutron excess, then those yields will change of freeze out from nuclear statistical equilibrium. And this is also relevant for neutrino processed material that was completely disassembled and then will have its neutron to proton ratio reset by neutrino absorption and emission processes that will also obey a similar mechanics really. Yeah. So if you have neutron excess of 0, so symmetric matter, you'll tend to make nickel 56. And the lower you go in your YE and the higher you go in neutron enrichment, the more you'll move to neutron-rich nuclei as the dominant nucleus in freeze out from nuclear statistical equilibrium. Yeah. So if you have a moderate neutron excess of about 0.07, then you'll make iron 56 directly. If your matter has even larger neutron excess, then you'll make you can even make unstable unstable isotopes. Yeah, very neutron-rich nickel or iron isotopes. You can make, for example, iron 60 here. Yeah, and if you had very extreme conditions, you'd make very strange nuclei, yeah, that you've probably never encountered before, 78 nickel and so on. Yeah, and for even higher neutron excess, we'll come to that later. You might make something completely different than nuclear statistical equilibrium. All right. One complication about freeze out in core collapse supernovae is, yeah, so on the one hand, it depends a bit what material you burn into NSE, into nuclear statistical equilibrium, and then undergoes freeze out later. So at the edge of your ion core, you have something of a neutron excess in the silicon shell. And that would imply that you get, yeah, some of these elements here. Yeah, you'd get, among other things, the 58 nickel, and that actually will make the nucleosynthesis a rather sensitive thermometer, really, for the conditions in the regions that underwent explosive burning, because one thing that you can measure in core collapse supernovae from their late spectra, so-called nebular spectra, is the ratio of iron to nickel, and that will be dictated by how much neutron excess you have. So if you had the 58 nickel here directly, which is stable, yeah, you'd get a different iron to nuclear to nickel ratio than if you burn the material at symmetric conditions. And actually, this imposes that most of the explosive burning that you do in a core collapse supernova can't happen at very neutron-rich conditions, because that would give you a wrong iron to nickel ratio. Yeah, and you can only really, so that actually tells us something very important about the explosion mechanism. You can actually only eject a tiny bit at best of the silicon shell and reprocess that by explosive burning, because otherwise your nickel to iron ratio would be off. And similarly, you couldn't actually eject directly any iron from the core. That would be in conflict with any nucleosynthesis yields that we can deduce. Yeah. Another special thing that can happen in core collapse supernovae is that the explosive burning can land your material in a region where there is rather high entropy, and then the freeze out from nuclear statistical equilibrium will look slightly different. It will be so-called alpha-rich freeze out. Yeah, what's special about alpha-rich freeze out? Well, in alpha-rich freeze out, what we basically do is, maybe make another sketch. Yeah. So in NSE, we are really we really have all the nuclear reactions in equilibrium. So assembling of neutrons and protons into alphas, and then the assemblage of alphas into carbon 12 by triple alpha reactions, and so forth. Yeah, alpha captures on carbon 12 to oxygen 16 and neon 20 and so on, and of course the inverse reactions too. Yeah. So the first of these reactions that tends to be cut is the triple alpha reaction. Yeah, that tends to freeze out at higher temperatures, especially if you have relatively low density. Why is that the case? So remember, the triple alpha reaction has is a 3-particle reaction effectively. So it has a steeper dependence on the density. Yeah, and if the density is very low, it's difficult to make a 3-particle reaction work. Yeah, So for that reason, if you're in the regime of, if you have relatively low density at a certain temperature, triple alpha is more likely to freeze out early. Yeah. And lower density at a given temperature means higher entropy. Higher entropy would also incidentally mean that you have many alphas sticking around in NSE in the first place, because you can at higher entropy make more of the less tightly bound isotopes. Yeah, that's the way the nuclear statistical equilibrium changes. All right, so now what happens if you cut the chain of reactions between alphas and the nuclei at carbon 12 and above? Well, at that point, the alpha fraction is in a sense fixed and becomes a parameter in the equilibrium within the heavy nuclei that are still being transmuted into each other by alpha captures, and if you have any side chains, also by neutron and proton captures or knockout reactions. Yeah. So under these conditions, what you basically get is that with the abundances of your heavy nuclei, heavier than carbon 12, are dictated both by the Boltzmann factor determined by the mass excess of a given nucleus, as well as by the alpha fraction. Yeah. And again, instead of just solving this mathematically, I will appeal to a more intuitive argument. So basically what will happen in this entire chain of reactions, yeah, so where you start from 26 magnesium, 28 silicon, 32 sulfur, and so on. Yeah. So generally what will happen is that the more alphas you have around, the more this will drive the distribution of the heavy nuclei towards the ones that tend to capture more alphas. Yeah, that tend to contain more alphas. Even if, let's say, this is unfavorable from the energetic point of view. Another complication actually comes into play here. So as the freeze out of these reactions in NSE proceeds, yeah, and you have several reactions here that connect the magnesium 24 and even neon, connect that to the iron group. Yeah, the next one is 48 chromium, I think. Yeah. 52 iron and so on. Yeah. One of the next reactions that will be cut will be the link between titanium 44 and the heavier nuclei. Yeah. And that means that once you're about to cut this reaction link and you have a lot of alphas around, then what will tend to happen that alpha captures will tend to move your abundance risk distribution somewhat into titanium 44, and the titanium 44 is a bottleneck where the reaction flow gets stuck. Yeah. So if you have this freeze out where you have many alphas around and you freeze out from NSE, then you can run into this situation that the material that wants to go from 28 silicon upwards by alpha captures can get stuck at 44 titanium, and you produce a lot of 44 titanium. And similarly, this is conversely, in the iron group region, what you will do if you have many alphas around during freeze out, you will tend to make nuclei that are a bit heavier than nickel 56. So you will tend to capture alphas on nickel 56 and its surrounding nuclei, and make nuclei of mass number 60 and above. Yeah, how things unfold with the neutron and proton captures that happen at the same time is a bit tricky, because there can be some reassembling. Yeah, so this is the reason, for example, why you can still make neutron-rich. You can still make isotopes of other isotopes of nickel by alpha captures, and then some neutron and proton captures, or neutron emission of neutrons and protons. But basically, what happens to the ion group nuclei in alpha-rich freeze-out is they will be shifted a bit towards higher mass number. Yeah, and this can make some rare isotopes like zinc 64. All right. This might probably be a good time to stop, pause briefly for questions. Continue. Yeah, then let's continue with the neutrino-heated ejecta. So with the neutrino-heated ejecta, the situation is somewhat similar to the freeze-out from nuclear statistical equilibrium, but in explosive burning. But now the electron fraction can be completely reset by the neutrino irradiation. So, and the same thing happens to the entropy of the material that is ejected by neutrino heating. So that has little to do with the entropy and electron fraction that this material had before collapse. Yeah, everything goes close to the neutron star, gets into the heating region, and the thermodynamic conditions are just completely reset. Yeah. So one important difference here is that this material always tends to be ejected with higher entropy than in explosive nucleosynthesis. That will have implications for the way the freeze out proceeds. Yeah. So you're more likely, you can be quite likely to get into this alpha-rich freeze-out regime, at least if your electron fraction is close to 0.5. Yeah, where you still have significant numbers of alpha particles around. Looks different in neutron-rich conditions. And the neutron to proton ratio will be reset by the captures of electron neutrinos and antineutrinos on neutrons and protons respectively, and by the corresponding electron or positron capture reactions. So as the material moves a bit away from the protoneutron star, it's the neutrino absorption reactions that dominate this equilibrium. And it's the competition between the captures on neutrons and protons that determines the YE. So you can work that out if you know the rough energy dependence of these reactions. So based on the luminosities and mean energies of the electron neutrinos and antineutrinos, you can work out how your YE will end up. And the upshot is basically that, well, if you have higher electron neutrino luminosity, or if you, sorry, let's do it the other way around. So if you have higher electron antineutrino luminosity and higher electron antineutrino mean energy, then this will tend to drive your YE down. Yeah, there's actually a bit of a complication there, because the proton to neutron mass difference would also come into play here if you took into account the terms of higher order in these in the dependence of the cross sections. Yeah, but basically the stronger the antineutrino luminosity emission is, and the more energetic the spectrum is, the more likely you'd be to encounter neutron-rich conditions in the neutrino-driven material. Yeah. The neutrino capture reactions, neutrino absorption reactions will of course freeze out at some point, yeah, when the material moves away from the source of the neutrino emission, and they basically freeze out when the time scale for the change of YE is comparable to the expansion time scale of the material. Yeah. And this also means that the faster neutrino-heated material expands, the earlier that freeze out will happen. And if you have very fast expanding material, then you can keep your YE lower. Yeah. The reason why you can keep it lower is, maybe I'll make a little drawing, is that, well, you get your, from the neutrino processing, nu E plus neutrons and nu E bar plus protons, you get an asymptotic value of YE that material would attain if you had it exposed to neutrino emission forever. Yeah. And in reality, the electron and positron captures also play a role, so that with neutron plus E plus and proton plus E minus goes to neutron plus nu E, and this goes to proton plus nu E bar. These electron and positron captures as a net effect tend to drive your YE down close to the neutron star. Yeah. And the further away you move from your neutron star, the less these capture reactions will matter because the density is lower. Yeah. And the more you will approach the asymptotic YE that you would have if you had just neutrino absorption along the way. And if your, let's say, if your neutrino, so the neutrino reactions will tend to bring the material upwards in YE, regardless of where this equilibrium YE is. Yeah. And if on this way to a higher YE, you freeze out at some earlier point, because the material has moved so far away from the neutron star, you might undershoot this asymptotic electron fraction in the end. Yeah. And the earlier the neutrino absorption freezes out, the lower the YE will be. Any questions on that? Now, what are the implications of that? Yeah, so as a result of this reprocessing of neutrinos, we get a complicated distribution of YE and entropy in the ejecta, really. This is a visualization from an explosion model of a low mass supernova, one of these electron capture supernovae that we mentioned in the previous lectures. And what you see here is this structure of the early neutrino processed ejecta. They come out in neutrino heated bubbles. And in this case, because the bubbles expand very fast, in some of these bubbles, you actually retain YE, which is plotted here on the left side of values below 0.5. Yeah. And the entropy in these bubbles varies quite a bit. Yeah. This will look different in more massive progenitors. In more massive progenitors, it tends to be more difficult to make YE lower than 0.5 in the ejecta. Yeah, but if you have parcels of neutrino-heated material that expand relatively quickly, or if you have neutrino emission that favors neutron-rich conditions, then you can make relatively high or moderately high entropy material with electron fraction less than 0.5. And this can then give rise to a freeze-out pattern from nuclear statistical equilibrium or quasi-equilibrium, where you make substantial amounts of nuclei heavier than iron or nickel. Yeah. So in this case, you make, for example, some rare, nuclei like strontium and zirconium, which are difficult to account for by other cosmic sources.
So Bernhard, in the left plot, what do the colors actually mean?
So in the left plot, the left part means the electron fraction. Yeah. The color scale is here. So blue is neutron rich. Green, yellow is symmetric, YE 0.5, and red is proton rich. You see the later ejecta are proton rich, and the right half of this plot is entropy, and red is the highest. Yeah.
Okay.
Okay. All right, and you also tend to see already in this plot here, during the later phase of the explosion, what tends to follow is a more spherical outflow. That's a wind outflow driven by neutrinos that ablate the neutron star surface, as it were. Yeah, and the same considerations apply here. So the neutron to proton ratio in this region will be set by the neutrino emission and by the expansion timescale of the material. Yeah. This neutrino-driven wind tends to contain very little mass in total. Yeah. So of the order of maybe a thousandth of a solar mass, but it has historically been speculated about as a possible source for very interesting nucleosynthesis, simply because this wind will tend to have relatively high entropy. And under these high entropy conditions, if you also have neutron-rich conditions, you could do rapid neutron captures and make stuff like actinides and so on in the so-called R process. Based on current models, we actually disfavor this for the simple reason that the neutrino-driven wind that we predict in models tends to be proton-rich and not neutron-rich. That's because the spectra of electron neutrinos and antineutrinos are relatively similar. So the electron antineutrino spectra are simply not hard enough to drive the YE down. And the entropy in the wind is also rather moderate. It would need to be a factor of a few higher to allow a nice rapid neutron capture process. So the entropy would need to be high simply because your freeze out from NSE should leave over a large fraction of neutrons per seed nucleus to capture them on. Yeah. And the energetically less favorable single particles, neutrons and protons, they will be more abundant in equilibrium if you have higher entropy. Yeah. You could, however, have then other sorts of capture reactions in the proton-rich outflows, these take on a very interesting kind. So the reaction flow tends to be rather intricate and subtle, and you might need neutrinos to bridge the gap of certain reactions that wouldn't occur easily without neutrinos. That leads to the so-called nu-p process, but this goes a bit more into the details than we can cover here. All right, but there might be other neutrino nucleosynthesis processes in rare forms of supernova explosions. So, for example, it has been speculated that in these magnetorotational explosions, which I mentioned on Wednesday, you could eject a lot of neutron or quite some neutron-rich material. The reason why you can keep material neutron-rich here is, well, you eject it with very large velocities, yeah, in jet outflows, and then because the neutrino processing is then slow by comparison with the hydrodynamical timescales, you retain the neutron excess that you have close to the protoneutron star, where the material comes from. Yeah. So this just comes with all the uncertainties that surround this scenario of hyperenergetic, possibly magnetohydrodynamically driven explosions with jets. We don't know yet how these work properly. We don't know the initial fields. We don't know many things about field amplification for sure. We are somewhat uncertain about the progenitors and how they retain the rapid rotation required to make these explosions. But if they do, they might eject matter under very neutron-rich conditions. And if you have lots of neutrons and a small number of seed nuclei, then you can capture those due to the high neutron flux and drive them far out of the value of stability, do many, many neutron captures before there is any decay. That's what makes this a rapid neutron capture process by definition. And then you make these R process elements that include, or isotopes that include, among other things, gold, that include the actinides and so on. Yeah, but many open questions surrounding this scenario. All right, and then we're basically finished with supernova nucleosynthesis. So if we now put everything together with what the progenitor made during hydrostatic burning, and you plot what is known as an overproduction factor. So you plot basically this. So production factor will be the mass of a certain isotope Za in your ejecta divided by the total mass of the ejecta, and you compare that to the mass fraction of these isotopes, of this isotope in the sun. Yeah. So if you have a production factor bigger than 1, you produce on average more of that material in terms of mass fraction than you have in the sun. And if you cycle material through stellar explosions, you will enrich the inventory of chemical elements in the galaxy with this element. Yeah. I'll come to the question in the chat shortly. And what you also expect is that if you have, let's say, a single source for a certain range of isotopes, they should have very similar production factors. Yeah, because in the end, you want to make in the solar inventory, chemical inventory, of course, these elements have a fixed mass fraction, fixed ratio of mass fractions. So if you have much more production of, let's say, one isotope, this let's say oxygen-16, you produce a mass fraction that's 100 times higher than oxygen-16 in the sun, but only 10 times more higher mass fraction of iron-56 in the sun, then your oxygen and iron in the sun can't all come from the source. They would converge to a different ratio of mass fractions. So if you want to predominantly produce a certain range of elements from a given source, like massive stars, they should have similar production factors. Yeah. So, and you find that you have large and similar production factors from massive stars after the supernova explosion for a large range of elements, starting basically from oxygen 16 in particular, yeah, to the intermediate mass elements. Then you get a bit of a deficit here in the iron group, yeah. So the production factors for the iron group elements are a bit lower. That's consistent with the fact that many of these are also produced quite abundantly by thermonuclear supernovae. Those will fill in this gap. And then you again have large production factors for some of these lighter elements, some of these first elements beyond iron, yeah. Among them, those that are made by this alpha-rich freeze-out. And you also get a bit of S-process elements, weak S-process elements that I mentioned yesterday. And you get a few isolated rare isotopes at higher mass that come, for example, from neutrino spallation processes and so on. Yeah. That's also responsible for this boron thing here. Okay. Yeah, and if you're interested in the details, this review by Woosley and collaborators from 2002 is really an excellent reference. Now, there was a question in the chat about the magnetorotational explosions. Yes, the question there was, can't the magnetic reconnection, which releases large amounts of energy, which can be used to conform the R theory? You mean R process theory, I guess, yeah. You're talking about a scenario that's quite interesting, yeah. So what might happen, but no one has really theoretical understanding that's good enough to confirm this. What might happen is that magnetic fields could also effectively heat material to very high entropies. Yeah, even if you don't have very neutron-rich ejecta, that might still modestly neutron-rich ejecta and strong heating by phenomena like alpha waves that could give you conditions for R process nucleosynthesis. But there's a lot of open question in theory behind that, and no one really can answer whether the R process occurs in core collapse supernovae reliably just with theoretical arguments at this stage. Yeah, there is circumstantial evidence really from observations of metal poor stars and the chemical history of R process enrichment in the universe. So some people argue that you cannot make all the R process elements from neutron star mergers at arbitrarily low metallicity, yeah, because the neutron star mergers always have to come after supernova explosions that have already enriched the environment with some metals. But these discussions are ongoing, yeah, whether there is any clear evidence for R process nucleosynthesis in some form of core collapse supernovae.
Bernhard, a related question. So could the spectra from the supernova not answer any of these questions?
Yes, some people have actually posited that. So there has been a suggestion that gamma ray, so that's hypernova light curves are powered by the radioactive decay of R process elements. If you look at the spectra proposed in this paper, they actually look nothing like the hypernovae that we observe. So in principle, if you had light curves with decay compatible with R process material, and if you had spectral lines corresponding to that, as you now seem to have for kilonovae from compact object mergers, then you could say this is a smoking gun for R process. But to my knowledge, we don't have that for any observed supernova explosions.
I see. There has also, I hear that some claims on long GRBs being the sites of our process.
Yes, yes.
Is it, what is the status of this claim?
Yeah, that goes in the same direction, really. Yeah. So this would be embedded in the same scenario. So it would be would connect the R process either to a magnetorotational supernova or to a collapsar type explosion, so outflows from an accretion disk, and the R process would be would happen either in the disk outflows or in the jet material behind the gamma ray burst. But yes, I think the observational confirmation is just lacking there. And the status of modeling there is really still somewhat shaky. The tricky thing is if you do something just slightly wrong in your model, in the way you treat the nuclear reactions or the processing by neutrinos, then you might retain neutron-rich conditions for an R process that will really go away if you treat things a bit more accurately. So I think this is still an ongoing debate. It's all very shaky. There might be something there. R process either in explosions driven by millisecond magnetars or driven by outflow from collapsar disks, but we have no final answer on that yet.
Hi, I have a question. So can you tell something about R processes in bounded ejecta of a binary neutron star or NSBH mergers?
In the R process in binary neutron star mergers, and you had...
Yeah, the bounded ejecta, the tidal disrupted matter that is around like...
Yes. So, I mean, in the binary neutron star mergers, you basically have two sources or two components that can contribute to our process. These are really, or maybe three, yeah. So you can have ejected material that's ejected by the tidal disruption of the lighter neutron star in a sort of spiral. You can have material that's squeezed out at the collision interface between the neutron stars. That will make a robust R process up to the highest mass number, so up to the third peak. To my knowledge, but I would probably have to look this up. To my knowledge, in the general relativistic simulations, it's really mostly the squeezed out material from the collision interface that you have, and the tails of ejected matter from the tidal disruption are either weaker or not really present in the relativistic models, but I might need to look that up. And then you have another component, which is either the disk around the remnant black hole or neutron star, or the hypermassive, the wind outflow from the hypermassive remnant. Yeah, and these later outflows, to my knowledge, they tend to make the more of the lighter R process elements. They might not reach the third peak, but the combination of those ejector components actually gives you a fairly good agreement with the solar R process pattern. Does that answer your question? I hope.
Yes, thank you.
Good. Yeah. Anything else on nucleosynthesis before we move on to discuss observed supernovae a bit? Okay, I'll move to the next bit then. So let's talk a bit more during the last half an hour about the observed supernovae and their phenomenology. And given that we only have very little time left, this, of course, is probably maybe a somewhat superficial introduction into the results from supernova observations. Bear that in mind, so we can't go very deep here. All right, so as there are the reference on observed supernovae is very extensive. A good starting point is just the book by Branch and Wheeler on supernova explosions. And I'll mention a few further references down the road. Now, already on Tuesday, I walked you through the rough classification of observed supernovae based on the lines that you see, and also based on the light curve shapes. This is the same thing, just with another scheme. So based on the spectra, you break the observed ones down into hydrogen-free and hydrogen-rich ones. Among the hydrogen-free ones, type 1s, you have with silicon-2 lines the 1As, which are thermonuclear and don't really concern us. Then you have stripped core-collapse supernova explosions 1B and 1C with and without helium-1 lines. Whether that means that we have no helium is another question. I'll come to that. And among the type 2s, we have a bit of a variety among spectral properties. So we have the 2Bs where the hydrogen lines later disappear. And we have ones, type 2s with different light curve shapes. And there are also some that have other special features like narrow lines. And among the 1Cs, we'll have a few that have very broad lines. And there's also a type 2 pecked peculiar explosions, an example of which was supernova 1987A. To illustrate this difference among the type 2s in the light curves in particular, this is an old figure from Wheeler. So what most type 2s have after a very short peak is a characteristic plateau where the bolometric luminosity over all wavelengths actually stagnates. The blue magnitude still decays, but you still have a visible bump here. Yeah, that's what we call the plateau. Yeah, whereas the 2Ls, of which there aren't very many, have a more linear decline during this phase. Yeah, and all of these types tend to have a more or less exponential tail, which it turns out is powered usually at least by the radioactive decay of nickel-56. Sometimes there might be breaks in between in the decay that has something to do on the one hand with how the conditions for the escape of positrons and gamma rays from the nickel-56 and cobalt-56 decay change. And at very late times in type 2p supernovae, you might have other sources taking over to power the light curves after many years, like the titanium-44 decay. Yeah. Supernova 1987A, which was the closest example of a type 2 supernova that we've seen recently, looks quite different. So you see it was quite a bit dimmer than the type 2s regularly are. And it didn't have this typical plateau here. Why that is the case is something that I'll discuss shortly. So about the statistics, how many core collapses fall into which category? So the majority are type 2s, and the 2Ps are really the most common ones. If you try, and this breakdown presupposes that we base the counts on a volume limited sample. So we disregard, so we factor out selection biases due to the fact that some of these explosions might be brighter than others, and we might be able to see them at larger distances. Yeah. The 1Cs tend to be a bit more numerous than the 1Bs. Most of them, there is also quite a bit of variations in the type 2s. So the type 2s in total really make up the vast majority, about 75% of explosions. Yeah, if you lump the two Ns and the two Bs and the two Ls together with the two Ps. Okay, now about the supernova light curve. So I'm going to explain the physics there a little bit. So why do the light curves look quite different? Yeah. So why this bump here for the type 2Ps, for example? So the physics of hydrogen, the light curves of hydrogen-rich supernovae is basically this. So if your supernova shock runs through the red giant envelope, the envelope will have been ionized, and you'll have free electrons around, and the photons will be trapped in this region by Thomson scattering. Yeah. What will happen later as the explosion expands is the material will cool down, your hydrogen will recombine. It does that at a roughly constant temperature, 4,000 or 5,000 Kelvin. Yeah. And as it recombines in the outer parts of the envelope, the radiation can escape from these regions easily, and the photosphere moves inwards in terms of mass coordinate into your envelope, into deeper regions. Yeah. And the luminosity that you see is basically given by the Stefan Boltzmann law with a changing emission surface, so a receding photosphere with more or less constant temperature, 5,000 to 6,000 Kelvin, and set by the radius of the photosphere. So with the structure of a type 2P supernova progenitor, the way this works out is that the photospheric radius doesn't change too much either, and the temperature is roughly constant. So for that reason, as this recombination wave proceeds through the hydrogen envelope, you maintain more or less constant bolometric luminosity. Yeah. And once you're through, the recombination of the hydrogen envelope is complete, you'll see a sharp drop off of luminosity. Yeah, as the photosphere recedes into the helium shell and even deeper. Now, people have worked out analytic scalings for the dependence of this plateau luminosity on the mass of the ejecta and the explosion energy and the radius of the progenitor. Basically, as expected, the more energetic your explosion, the higher the luminosity, and the dependence on progenitor radius and mass is probably not so easy to guess. The less mass you have, actually, the brighter the explosion will be. And the larger the radius, the brighter the explosion will be. And you can also infer similar scalings for the duration of this plateau on ejecta mass and explosion energy. Basically, the plateau phase will last longer if your hydrogen envelope is bigger. So this is nice because it allows you, based on photometric properties, the brightness and duration of the plateau, to piece together, to roughly constrain the explosion properties of the star, supposing that you know the progenitor radius from stellar evolution models. Yeah. So quite interestingly, the typical plateau luminosity, plateau duration in type 2P supernovae tends to be relatively uniform. It tends to last for about 100 days or so. Yeah. So with that, we can work out the distribution of explosion properties in type 2p supernovae. What we find is that the explosion energy probably scatters about 2 orders of magnitude, from 10 to the 50 ergs to 2 times 10 to the 51. 10 to the 51 is about a typical value. And there's similarly a broad spread of nickel mass. The nickel can be then inferred from the brightness of this tail. Yeah, the nickel mass is of the order of a few hundredths of a solar mass, but also varies quite a bit. And interestingly, there seems to be a correlation between both the nickel mass and the explosion energy, and also with the progenitor and ejecta mass. So the more massive stars tend to explode with higher energy. Pinning down masses and explosion energies for individual type 2s can be a bit more shaky though, because these relations for luminosity and plateau duration leave a degeneracy between ejecta explosion energy and ejecta mass. That's why all these error ellipses have this somewhat diagonal shape. Yeah, but still, they can't all have the same progenitor mass, so there must be a correlation underlying this distribution here. Yeah. What about their progenitors? I also mentioned that quickly already on Tuesday. So the progenitors of type 2p supernovae, some of those have actually been directly identified based on archival images. They are red supergiants, and based on the brightness of their pre-explosion images and comparing those to HR tracks in the HR diagram, you can actually put masses on them. That's helpful because it helps break the degeneracy on mass that you have from light curve modeling. And this leads to the recognition that probably there is a cutoff with most in supernova explodability, with most massive stars, red supergiants of an initial mass more than about 18 solar masses should not explode. Yeah, what you see here is basically the distribution, the observed cumulative distribution of exploding massive stars and what you would expect if all of them exploded. That's the dashed curve here. Yeah, and there seems to be a significant statistical discrepancy. In recent years, we have actually had probably some positive confirmation that some of the more massive red supergiants indeed do not explode. There's a group that has been monitoring galaxy images for disappearing red supergiants, and one such red supergiant has been found. Seems to indicate the disappearance of a star with an initial mass of 20 solar masses on the main sequence. So that's more confirmation that among the red supergiants, there's probably something like a cutoff or a tapering off of the probability for explosion at higher mass. Okay, now let's connect this back to theory a bit. So based on what we have learned in the previous lectures on the structure of massive stars, we know that the initial mass of the star is reflected in the core structure. Yeah, more massive stars tending to have bigger cores with a higher compactness parameter, bigger oxygen shells, and so on. And we also discussed that if stars explode, they will tend to have higher explosion energies if they have more massive cores and oxygen shells. So the 3D supernova simulations are not so efficient yet that they can systematically scan parameter space very finely, but simpler approaches which are compatible with what we know from the more sophisticated simulations have been done to predict, or at least retrospectively understand, the explosion properties of massive stars. And they quite naturally account within the idea of the neutrino-driven mechanism for exactly those patterns that we see in observations. So a correlation of explosion energy and progenitor mass, nickel masses of a few hundredth of a solar mass, and probably a dearth of explosions at higher progenitor mass. This might not be an exact cutoff. It might be a transition to very few explosions above 20 solar masses, but a few islands of explodability at higher masses, and maybe also a few instances of black hole formation at relatively low mass here. Yeah. So this has been addressed with different theoretical approaches, but they all find a very, very similar distribution. And this gives us some confidence that the neutrino-driven mechanism is indeed what governs the explodability and what explains the energetics of the observed supernova population. Okay. Now, quick detour on supernova 1987A. So 1987A had a light curve that looked very different, as I showed you before. Yeah. Let's go back to that quickly. Yeah. So it had this dome-shaped light curve. Yeah. And wasn't very bright. So that follows naturally from the fact that the progenitor, which we had observed before, was a blue supergiant. Yeah. So under these conditions, you will not get a bright plateau. Yeah. For such a very dim quasi-plateau, what will matter is that the radius is really the additional energy input from radioactive decay that starts to heat your photosphere even while the recombination front is still in the hydrogen envelope. Yeah, so this explains why there was this rise in the dome-shaped light curve of supernova 1987A before the plateau, before the tail, which is then purely powered by the decay of nickel. Yeah. So in terms of the progenitor, it was inferred that this was probably between 15 and 20 solar masses, had an explosion energy upwards of 10 to the 51 ergs. Oh, there's a typo here. This should be 10 to the 51, not 10 to the 50. It had some interesting features in its environment as well. So there was ring-shaped circumstellar material, a triple ring structure, and you can put many of these peculiar features together and explain them coherently if supernova 1987A was actually the result of a binary merger. That would naturally explain why the progenitor was blue. Yeah, it would explain why there was this circumstellar material, and that's basically what I wanted to say about supernova 1987A. There's a small fraction of type 2 supernovae that also come probably from the same class of exploding blue supergiants. So about 1 to 3% look similar, coming apparently from compact progenitors, being not very luminous, although having normal explosion energies. All right, now let's move on to the other big class, the 1Bs and 1Cs. So they have no hydrogen in their spectra, indicating that they were stripped of their hydrogen envelope. This will imply that the physics of the light curve is different. The light curve will be powered by the decay of nickel 56 all the way, yeah, without such a plateau. You can use the light curve properties similarly to type 2Ps to infer some explosion parameters. So it was already predicted many years ago, 40 years ago, that under these conditions, the peak luminosity is basically related to the decay power from radioactive nickel-56, hence the nickel mass, at the time of the peak of the light curve. But this is something of an approximation and makes estimates of supernova 1bc nickel masses a bit shaky. This rule, Arnett's rule, tends to work well for thermonuclear supernovae, where the nickel is fairly homogeneously distributed in the ejecta, but not so much for the type 1bcs. And probably many of the nickel masses that are quoted in the literature are somewhat overestimated for that reason, by 50% or so. Yeah. How much mass you eject and how much explosion energy you have tends to affect how fast the light curve evolves. So whether it's you have a wide peak or a narrow peak, so faster expansion, higher explosion energy will tend to make the peak more narrow. Higher ejecta mass will tend to make it make the peak, the light curve, broader. And again, you see when it comes to determining the explosion energies and ejecta mass, there's again something of a degeneracy if we tie those parameters to the width of the light curve. Yeah. But nevertheless, there are some findings about 1bcs that seem somewhat robust. So if we explain the light curves by the decay of radioactive nickel, then they would have to have somewhat higher nickel mass than the type 2Ps on average. It has recently been questioned whether the light curves are exclusively powered by the decay of nickel-56, and that there might be some need for energy input by the spin down of the neutron star. But that's a matter of current debate. Again, estimates of ejecta masses are shaky, but you can break that degeneracy somewhat by looking at spectral lines in different phases. And what has emerged over the last years is that the ejecta masses often tend to be relatively low, at least too low to make them compatible with an explanation of 1bcs coming from Wolf-Rayet stars. And that, together with the fact that we have quite many of these 1bc supernovae, has led us to the conclusion that most of the 1bcs really have undergone stripping in binary systems. There is an interesting open question, though, about the nature of the 1Cs versus the 1Bs. So the 1Cs have no helium lines, but as I hinted at before, that doesn't necessarily mean that they have no helium. It could simply be that there is no non-thermal excitation of the helium to make those lines. That depends very much on how the mixing of nickel-56 works in these explosions. And yeah, that remains an open question. What's really the difference between 1Bs and 1Cs? Now, there was a question in the chat that I would probably need to address here. Questions about supernova 1987A. Yes, so there was an open question about supernova 1987A, whether under which circumstances we can expect a compact envelope like supernova 1987A only from stellar mergers. Well, the answer is that you have that whenever your star undergoes a blue loop on the HR diagram. Yeah, it's caught in a blue loop while it explodes. So the blue loops can be sensitive to other physics as well, like the metallicity of the star. So there are possibly other explanations for getting a compact progenitor at the time of collapse without invoking binary interactions. Now, the second part of this question was, do we know about how merger affects core envelope structure? Oh, that probably would take a very long time to answer because the answer is complicated because that all depends on when the merger happens. So if the merger happens very late, then you probably only add mass to the envelope without affecting the core structure. If the merger happens early, then you might completely change the core structure as well. Yeah. So the simplest answer is probably to say it depends on when the merger occurs. Yeah. Okay, the cores merge. Yeah, that's another scenario. If you have depending on the mass ratios, yes, you might get into scenarios where you actually merge the stellar cores. If you have specific outcomes of common envelope evolution, I would probably say that all possible kinds of scenarios are on the table for the binary evolution experts. Yeah, the final part of your question here was whether the light curves can determine the envelope mass. Yes, as I hinted, to some extent they can, because both envelope mass and explosion energy and progenitor radius affect the light curve brightness and shape, but there are some degeneracies there. So light determinations of the ejecta mass by the light curve alone tend to be a bit shaky and subject to because of parameter degeneracies. I hope that answers that question. Okay, good. Now back to the 1BC. So I told you something about what we can learn from 1BCs, that they probably produce more nickel than the type 2Ps. Still unknown why that might be the case or whether there might be another power source. And we're still sort of struggling to understand what really distinguishes the 1Cs from the 1Bs actually. Now, there's a very, very intriguing subclass of the 1Cs, always 1Cs, which are characterized by broad emission lines, very broad lines, emission and absorption lines. This will indicate very high expansion velocities, and that implies, again, very high explosion energies, probably up to the ballpark of 10 to the 52 ergs. Some of these have been associated directly with long gamma ray bursts. Yeah, so we know there is an association there. And based on other observational constraints, so polarization, for example, polarization measurements during various phases, we have strong evidence that these have not only the gamma ray burst jet sometimes as a bipolar component, but also the slower non-relativistic ejecta components are bipolar. Yeah. We know that these are quite rare in the local universe, but they become more frequent at higher metallicity. And we basically have two favored scenarios that might account for these physically. Yeah, we already came across these. So it could be that you have either a rapidly spinning neutron star that makes jet-driven outflows, or it could be that you have an accretion disk around a black hole, and you launch outflows from that. So this would be called the collapser scenario. I can't go into these in any depth here. I just want to sort of complete the landscape, the map of supernovae that we know. Wrapping that up in just a few more minutes, I think. The most extreme case that has made some headlines in recent years are superluminous supernovae. So superluminous supernovae with absolute magnitudes, peak magnitudes less than 10⁻20 or so, yeah, or more, considerably brighter than any 1A, and about at least 2 orders of magnitude brighter than normal core collapses, are rather rare occurrences, probably 1 in 1,000 in the local universe or less, but again seem to increase in frequency in the in low metallicity environments. There are probably several mechanisms at play making them. The one subclass that we best understand among these are the hydrogen-rich superluminous supernovae. Most of these are 2N, so type 2 supernovae with narrow emission lines. Narrow emission lines indicate that you have cooling by emission of significant amounts of circumstellar material that was shocked. That's a very efficient way to convert kinetic energy into luminosity. And you can explain the type 2Ns best physically by assuming that you had some eruptive mass loss events before the supernova. How that might be the case, we'll discuss on the next slide. And for the remaining ones, the type 1 superluminous supernovae without hydrogen, as well as a few superluminous type 2s that don't have these narrow line features, the interpretation of the power source for the light curve is a bit more open-ended at this stage. So the ones that involve CSM interaction, clearly the type 2Ns, also have some other features that indicate that there might be circumstellar material. For example, they tend to have bumps and steps in their light curves that you could associate with the shock running through various shells of circumstellar material. And you can imagine several sources for massive CSM outside your supernova progenitor. It could be eruptions from luminous blue variables, which we don't understand very well theoretically, or these could be these shells could have been ejected by pulsational pair instability in very massive stars. Yeah, and then you have either another pair instability pulse, another shell running in through these other shells, or you have a core collapse finally, and the supernova runs through these shells that were ejected before. Yeah, and that would give you very bright light curves from CSM interaction. Already when superluminous supernovae were first seen, it was also hypothesized that they might be powered by nickel 56. Yeah, so you could explain very bright light curves if you had several solar masses of nickel 56. How could you make those? Well, you could make those in a real pair instability supernova. Yeah, so one big collapse and explosion that burns several solar masses of oxygen and carbon into nickel, and that releases tremendous amounts of nickel 56 and makes a very bright light curve. The problem with that interpretation, though, is that most superluminous supernovae have a faster rise than is compatible with this scenario. So if you want to make pair instability supernova and produce lots of nickel, this will tend to give you a very slow rise of the light curve because the opacity and optical thickness of the material is extreme. And the spectroscopic features also argue against the production of loads of ion group material in these superluminous supernovae. So that casts some doubt on whether any of these is really a pair instability supernova. Now, another scenario which has been thrown into the ring quite often, especially for the type 1 superluminous supernovae, are long-lasting central engines that input energy into the light curve. So this could be the spin down of a rapidly rotating magnetar, or it could be that you have a black hole disk that survives for a long time and is fed by fallback accretion. yeah, over days and weeks. Yes, so that's very open-ended because and still quite uncertain, because very often you don't have really good information to pin down what the physics behind the light curve is. You might just have the photometry and not much else. Yeah, so that's a subject of ongoing research. One problem, or one caveat about the explanation of superluminous supernovae with the spin down of millisecond magnetars, which I should flag, however, is that if these are powered by millisecond magnetar spin down, these magnetars must be something very different from the magnetars that we know. So the magnetars that we know are quite frequent. 10% of all neutron stars at least are born as magnetars, and they're associated with fairly normal supernova explosions based on their remnants. So medium explosion energies, no clear sign of energy input into the remnant or so on. So whatever these millisecond magnetars might be, you have to explain in what sense they're different from the normal magnetars and why the normal magnetars don't make these superluminous supernovae. Apparently, that would make 10% of all core collapses superluminous. There has to be a factor that explains that, why normal magnetars don't power superluminous supernovae. There has to be something different in there. Yeah, something special about the type 1 superluminous supernovae supposedly powered by magnetars. All right, and I want to conclude really by tying this back a bit to gravitational wave observations, because the question of when and if pair instability supernovae happen is really also being posed to us by other observational data. So stellar evolution theory told us initially that we'd expect these in this pulsational pair instability and pair instability regime, that we should not make any black holes between 50 and 130 solar masses. Yeah, so in the pulsational pair instability regime, you're supposed to bring down the progenitor mass by pulses until you make a normal core collapse supernova. Yeah, that's among other things what will determine this lower threshold for a black hole mass gap. And above, at higher masses, you'll get successful complete disruption of the star by a pair instability supernova. And then at some higher threshold in mass, you again form black holes because the pair instability does not lead to an explosion anymore. Now, those predictions of a black hole mass gap in this region have recently been challenged both by gravitational wave observations of among DW 1905-21 with a black hole mass in this supposed gap, as well as by electromagnetic observations. But stellar evolution theory has laid the cards on the table quite openly and said that both the lower and upper mass of this supposed gap are probably still somewhat uncertain for many different factors because of the possible impact of rotation, uncertainties in the nuclear burning, and so on. And that really implies, though, that we are somewhat in the dark about when and if pair instability supernovae happen. The black hole mass gap that we were supposed to see wasn't there, at least not in that region. Among the supernova explosions, we have no compelling evidence that we have ever seen for certain a pair instability supernova. And there's another smoking gun for pair instability supernovae that we haven't found. So pair instability supernovae in the early universe would have produced characteristic nucleosynthesis yields, basically a lot of enhancements in alpha elements. So even Z elements. and such abundance patterns of the ashes of these explosions have never been found in very metal poor stars yet. So the question, are there any pair instability supernovae, is still open. The chase, the quest for these things continues. So maybe someone here in the audience can find the first real evidence for a pair instability supernova from supernova light curves or black hole binary systems or whatever. Yeah, so have fun with that. I give you that as a challenge. So I hope you enjoyed those lectures somewhat, despite the density of the material, and you can use some of it for productive research.
Thank you very much, Bernhard, for this great series of lectures. They covered a lot of ground, starting from a pedagogical introduction to stellar structure and evolution, and ended up with covering the state of the art in supernova modeling and observation. So it was a fantastic resource for all of us, but not only for all of us, but also we hope that it'll be useful for students and young researchers across the world. So thank you very much. And of course, there is
Yeah, well, it's just a pity that I couldn't be there in person. It's still a bit difficult, but certainly another time.
Yes, so we are continuing the schools every year, so we hope to have you back some other time, and hope to see you in Bangalore sometime in the near future.
Good. Okay. Actually, still got a long question in the chat. I probably answer that in the chat. Good. Thank you.
So we can take a few more questions if there are any. Okay.
Yeah. Hi. So in one of your slides, you showed this pie chart about the different populations of different types of supernovas.
Do you mean the pie chart?
Yes. So can you please elaborate on this plot a bit, like how these pie charts are exactly obtained, like what kind of data that goes in obtaining these plots?
Yeah. So these were based on photometry, so just observations of magnitudes in various spans from a volume limited sample, the LOSS survey at the Lick Observatory. So they were monitoring transients and weeding out any outside a certain survey volume. Yeah, so that they catch even the faint ones. And then they just classify these and lay down the statistics. Does that answer your question?
The ejection of jets due to bipolar magnetic fields, is it trivial to say that the ejection will be always equal from both the sides, or could there be a preferred direction?
Yes, that's actually a very good question. It's not trivial at all, especially since, so if you look at this from the perspective of engine modeling, in models of bipolar jets, we find that the jets are sometimes affected to various degrees by magnetohydrodynamic instabilities. So example, like a kink instability. Yeah. So similar to what you're battling in plasma confinement in fusion research. And if such instabilities occur, they will not necessarily affect your two jets equally. And one of them could be stronger than the other. So it's very conceivable that they are in generally not always symmetric.
So are we able to model these things nowadays?
We are, yes, yeah, people are modeling these things nowadays. It's still not a unified modeling pipeline in the sense that you need somewhat different methods and tools for, let's say, the early phases of jet evolution and for a relativistic gamma ray burst jet, because the hydrodynamical or magnetohydrodynamic regimes require somewhat different methods. Yeah.
a few more questions from the basic properties of neutron stars, that these spin and magnetic poles are not aligned there. And do we have a pointer from Supernovae to think about, like
why the fields are not, the dipoles not aligned with the spin axis? Yeah.
Yeah. So can we, are we also looking into the properties of supernovae to like map to what neutron stars are having now, like what we are observing in neutron stars?
Yes. Yeah. This is becoming more active research, especially considering more how magnetic fields in neutron stars come about. Again, it's very difficult to bridge the various evolutionary phases. So what we are doing nowadays more routinely is to follow the field amplifications through collapse and through the early explosion phase. But then it becomes difficult to relate that to the phase where the outside of the neutron star is evacuated and the magnetic fields dominate the energy density. You enter into what is known as the force-free regime. Again, you need different methods for that. And so there are still a lot of challenges in bridging this gap, but people are working on that and trying to understand, let's say, do we naturally expect that magnetic fields, the dipole magnetic field that's formed by amplification processes in the neutron star or dynamo, so that this is misaligned with the rotation axis. And there are some simulations that are seeing that. Some of them actually still unpublished, but that will come.
And lastly, the recent nicer observation has shown that the hotspots due to magnetic fields are very weird. It's like quite heavily deviating from the bipolar magnetic field in neutron stars. So they have seen weird distribution of hotspots in one hemisphere itself.
Yeah.
And are we nowadays looking into, I mean, the same question again, like, are we trying to see something, a bridge from the supernovae or?
Yes, yeah. And there is actually a lot of potential here to learn from things like these nicer observations, because one thing which the more recent simulations are telling us is that we do not expect magnetic fields to be just dominated by a dipole. There's a lot of small scale structure in the magnetic fields that we expect. And this actually ties in exactly with what you said. And understanding the small scale magnetic field structure beyond the dipole that you can measure by spin down, that's a very important question also for the theory. Yeah.
Oh, all right, thank you.
Okay.
Yes. Could you please go to the slide on type 2p supernovae light curves?
1 second, I have to share my screen again. I had a few different ones. I mean, this one here.
Yeah. So could you please give some physical intuition for the plateau luminosity scaling with mass? Why does it go inversely?
The simple intuitive explanation, I'm probably somewhat hard put to say something about that. This will come about if you, so one thing that will, I think I'm actually asking you to rationalize some of this in the tutorials a bit. This comes into play when you, so what the explosion energy really fixes is the amount of thermal energy in the ejecta at a given stage, so close to shock breakout. And then the mass, what will the mass do? Yeah, probably hard to put this together directly. Yeah, I don't think there's really a nice intuitive explanation that I can come up with right away. This drops out if you put a number of, if you really put the diffusion equation and the first law of thermodynamics and the opacity scaling of the the scaling of optical depth together, I don't think I have a really intuitive explanation right away. There is a regime where you see this more clearly. So if you have a shock that runs into optically thin material, yeah, and heats that, then the thinner that material, the higher the temperature you will reach, because the shock velocity will be higher. And that will make actually stronger emission from cooling. But this is not something that you can directly transfer to this regime of the propagating recombination front.
Hello.
Yes.
Also, I just wanted to know, like, as people are interested in these mass gap events right now, so can you please briefly tell about the preferred origin mechanism that people talk about for supermassive black holes after this 130 solar mass, or say 200 solar mass, that black holes, the preferred?
This one here, yeah, where you had 150 solar masses in total and probably 65 and 85 or something. Yeah, this might be a somewhat a subjective take. I don't really think there is any preferred explanation from the stereo evolution point of view. People have just a number of hypotheses, all of them equally plausible or implausible. So it could be related to uncertainties of nuclear reaction rates. It could be some more complex interaction in this binary beforehand. I don't think there's any preferred explanation yet. The time since this discovery is still too short for us to be certain on anything.
Is it anyway with the what we know, like in pair instability supernova, the photons make electron positron pair, and that way in the radiation pressure decreases, so it explodes. But for why not this is acceptable for black holes with 150, say 200 solar mass? So
you mean what do you mean why the more massive ones don't explode as pair instability supernova?
Yeah, I mean, why people are interested, I mean, how people are defining these mass gap events, like only for, and there is controversy in the mass gap region also, like some people say it's 65 solar mass to 155 solar mass also. Yeah.
Basically what just happens if you go to very high mass, you'll ignite the oxygen too late. The collapse is already too far underway, and by that time black hole formation is inevitable. So it's a competition of the ignition of nuclear burning and the relativistic effects that come into play. So you know that it's basically easier for higher mass objects to form a black hole. The higher mass objects, for the same compaction m over r, they will have lower density. Yeah. And if you go to higher mass, then basically the oxygen burning will that would turn the explosion around occurs too late.
Okay, I don't see any further questions.
Yeah. There's a long question in the chat. I'm probably going to answer that in the chat, I think. Good.
Okay. Yeah. Yeah, so but this is a good time to remind people here that the course hasn't really ended. We are going to have tutorials in the afternoon where we are going to actually discuss some of these issues that was come up in the question and answer sessions. But before we break for lunch, let's give Bernhard a big round of applause. Thank you very much, Bernhard, for taking your time off.
Thank you for the invitation. Thank you
very much. Okay, then we will, people here on the Zoom land would come back at 2:15, the Indian Standard Time, for the tutorials.